Rogue planets. Rogue planets represent one of the most unsettling phenomena in space. These are planetary bodies that have been ejected from their original star systems and now drift alone through the cold darkness of interstellar space. Unlike planets in stable orbits around stars, rogue planets receive no warmth or light from any nearby stellar source. The ejection process typically occurs during the chaotic early formation of planetary systems. When multiple large planets form close together, their gravitational interactions can become unstable. The smaller or less massive planets get flung outward at high velocities, sometimes reaching speeds of hundreds of kilometers per second. This gravitational slingshot effect launches them completely out of their birth system. Once ejected, a rogue planet enters a state of perpetual cosmic exile. Its surface temperature plummets to near absolute zero, around minus 270 degrees Celsius. Any atmosphere it once possessed either freezes solid or gets stripped away by the harsh conditions of interstellar space. The planet becomes a frozen, lifeless world drifting through the void. Scientists estimate that rogue planets may actually outnumber stars in our galaxy. Current models suggest there could be billions or even trillions of these wandering worlds scattered throughout the Milky Way. Most remain completely invisible to our telescopes because they emit no light of their own and reflect no starlight. The terrifying aspect of rogue planets lies in their unpredictability. These massive objects move through space on trajectories that bring them dangerously close to star systems without warning. If a rogue planet were to pass through our solar system, its gravitational influence could destabilize planetary orbits, potentially ejecting Earth from its comfortable position around the Sun. Interstellar voids. Interstellar voids are vast regions of space that contain almost no matter whatsoever. These cosmic deserts stretch across hundreds of millions of light years, creating enormous bubbles of near-perfect emptiness within the universe's web-like structure. The most famous example is the Boötes Void, discovered in 1981, which spans approximately 330 million light-years in diameter. To understand the scale of these voids, consider that a typical region of space this size should contain around 2,000 galaxies, based on the universe's average density. Instead, the Boötes Void contains fewer than 60 galaxies. This represents less than 3% of the expected galactic population, making it one of the most underpopulated regions ever discovered. The formation of these voids likely occurred during the early universe when matter began clustering under gravitational influence. As dense regions attracted more material, they left behind increasingly empty spaces. Over billions of years, these empty regions expanded as the universe itself expanded, creating the massive voids we observe today. What makes interstellar voids particularly unsettling is the complete isolation they represent. If you were somehow transported to the center of a large void, you would see no galaxies, no stars, and no sources of light in any direction. The nearest galaxy could be hundreds of millions of light years away, making it invisible to the naked eye. The darkness within these voids is absolute. Unlike the space between stars in our galaxy, which still receives light from distant stellar sources, the interior of a cosmic void receives virtually no electromagnetic radiation. The cosmic microwave background radiation, the faint afterglow of the Big Bang, would be the only detectable energy source. Hypergiant stars. Hypergiant stars represent the most massive and unstable stellar objects in the universe. These cosmic monsters contain between 100 and 300 times the mass of our Sun, making them so large that they could engulf the entire orbit of Mars if placed at the center of our solar system. The extreme mass of hypergiant stars creates internal conditions of unimaginable violence. Nuclear fusion reactions in their cores proceed at rates millions of times faster than in normal stars. The immense gravitational pressure required to sustain these reactions generates core temperatures exceeding 100 million degrees Celsius. Despite their enormous size, hypergiant stars have extremely short lifespans. While our Sun will burn steadily for approximately 10 billion years, a hypergiant star exhausts its nuclear fuel in just a few million years. This rapid fuel consumption makes them incredibly unstable and prone to dramatic changes in brightness and size. The surface of a hypergiant star experiences constant upheaval. Massive convection currents transport energy from the core to the surface, creating turbulent regions larger than entire solar systems. These stellar storms can eject material equivalent to Earth's mass in a single outburst, creating expanding shells of hot gas around the star. The most terrifying aspect of hypergiant stars is their inevitable fate. When they exhaust their nuclear fuel, they undergo catastrophic core collapse, followed by a hypernova explosion. This explosion releases more energy in seconds than our Sun will produce in its entire lifetime, creating gamma-ray bursts that can sterilize planets across vast distances. Magnetar fields. Magnetar fields represent the most powerful magnetic environments in the known universe. These neutron stars possess magnetic fields that are quadrillions of times stronger than Earth's magnetic field, creating regions of space where the fundamental properties of matter and energy become severely distorted. The magnetic field strength around a magnetar reaches approximately 10 to the 15th Gauss, compared to Earth's field of roughly half a Gauss. This extreme magnetism is generated by the rapid rotation of the neutron star's incredibly dense core, which contains more mass than our Sun, compressed into a sphere only 20 kilometers across. Within the magnetosphere of a magnetar, atoms themselves become elongated and distorted. The magnetic field is so intense that it forces electrons into highly excited quantum states, creating exotic forms of matter that cannot exist anywhere else in the universe. The field lines become so tightly wound that they can snap and reconnect violently, releasing enormous bursts of energy. These magnetic field reconfigurations produce starquakes that crack the neutron star's crust, releasing more energy in a tenth of a second than our Sun emits in 100,000 years. The resulting gamma-ray bursts can be detected across the entire galaxy and would be lethal to any life within several light years of the magnetar. The space immediately surrounding a magnetar becomes a zone where normal physics breaks down. Photons split into multiple particles. Vacuum itself becomes birefringent like a crystal, and the very structure of empty space becomes twisted by the magnetic field's influence. Wolf-Rayet star environments. Wolf-Rayet star environments represent some of the most violent and unstable regions in the galaxy. These massive stars, typically containing 20 to 50 times the mass of our Sun, have reached such advanced stages of evolution that they continuously blast away their outer layers at speeds exceeding 2,000 kilometers per second. The stellar winds from Wolf-Rayet stars are so powerful that they strip away several Earth masses of material every year. This constant mass loss creates expanding bubbles of superheated gas and plasma that can stretch across dozens of light years, clearing out vast regions of interstellar space around the star. The surface temperature of a Wolf-Rayet star exceeds 50,000 degrees Celsius, making it hot enough to ionize any material within its vicinity completely. The intense ultraviolet radiation emitted by these stars is so energetic that it can strip electrons from atoms hundreds of light years away, creating massive ionization fronts that propagate through space. These stars exist in a constant state of instability, with their outer layers being continuously ejected, while their cores contract and heat up. The stellar winds carry away not just hydrogen and helium, but also heavier elements like carbon, nitrogen, and oxygen that have been forged in the star's nuclear furnace. The environment around a Wolf-Rayet star is completely hostile to any form of matter or life. The combination of intense radiation, high-speed particle bombardment, and extreme temperatures would instantly vaporize any solid object that ventured too close. Even at distances of several light years, the star's influence would strip away planetary atmospheres and sterilize entire solar systems. Sagittarius A star region. The Sagittarius A star region at the center of our galaxy represents one of the most extreme gravitational environments accessible to human observation. This supermassive black hole, containing approximately 4 million times the mass of our Sun, creates a zone where space-time is warped beyond normal comprehension. Within the innermost stable circular orbit around Sagittarius A star, space and time become so distorted that normal concepts of distance and duration lose their meaning. Objects orbiting at these distances experience time dilation effects so severe that time passes significantly slower relative to observers at safe distances. The region immediately surrounding the black hole is filled with superheated plasma spiraling inward at velocities approaching the speed of light. This accretion disk reaches temperatures of millions of degrees, emitting intense X-rays and gamma rays that would be instantly lethal to any form of life. Tidal forces near Sagittarius A star become so extreme that they would stretch and compress any object into long, thin shapes in a process called spaghettification. The difference in gravitational pull between an object's head and feet would be so great that molecular bonds would be torn apart long before reaching the event horizon. The gravitational influence of Sagittarius A star extends throughout the galactic center, controlling the orbits of thousands of stars within the central parsec. Some of these stars follow highly elliptical orbits that bring them within a few hundred astronomical units of the black hole, subjecting them to gravitational forces that distort their shapes and strip away their outer layers. Dark matter halos. Dark matter halos represent the invisible skeleton of the universe, the vast unseen architecture that holds galaxies together and defines the cosmic web itself. Every galaxy, from the tiniest dwarf spheroidals to the titanic spiral systems like the Milky Way, is embedded within a massive, invisible sphere of dark matter, a substance that neither emits, reflects, nor absorbs any form of light. And yet, despite being completely undetectable by conventional telescopes, dark matter outweighs all visible stars, gas, and dust by a factor of 5 to 1. Its existence was first inferred from a cosmic inconsistency. In the 1970s, astronomer Vera Rubin observed that galaxies were rotating far too fast for their visible mass to hold them together. By all known laws of gravity, the outer stars should have been flung into intergalactic space. Instead, something unseen, something massive, was binding them in place. This invisible mass was later termed dark matter, a name that captures both its nature and its mystery. A dark matter halo is not a simple shell surrounding a galaxy. It is a sprawling, three-dimensional distribution of gravitational power, extending far beyond the luminous boundary of the galactic disk. If the Milky Way's bright spiral arms span about 100,000 light-years, then its dark matter halo stretches almost 2 million light-years across, 20 times larger and nearly spherical. Within this ghostly sphere, billions of solar masses worth of invisible particles orbit silently, forming a kind of gravitational cocoon that anchors every star, planet, and cloud of gas within our galaxy. Computer simulations of cosmic structure formation reveal that dark matter halos are not smooth or uniform. They are filled with filaments, subhalos, and smaller clumps that behave like invisible satellites orbiting larger halos. These substructures can pass through regions of ordinary matter, subtly distorting the paths of stars and comets without leaving any visible trace. Some astronomers suspect that unexplained anomalies in the orbits of long-period comets, or in the trajectories of interstellar visitors, could be the faint fingerprints of these dark subhalos passing nearby. The nature of dark matter itself remains one of science's most haunting mysteries. It does not interact with electromagnetic radiation, meaning it cannot be seen, touched, or measured directly. It does not collide or scatter like ordinary atoms. The particles that compose it might pass through an entire planet without ever interacting with a single atom of normal matter. Despite decades of experiments using ultra-sensitive detectors buried deep underground, scientists have yet to detect even one confirmed dark matter particle. Some theories propose that dark matter consists of weakly interacting massive particles, WIMPs, relics from the early universe that barely interact with anything else. Others suggest more exotic explanations, such as axions, sterile neutrinos, or even entire populations of microscopic black holes left over from the Big Bang. Yet no theory has proven definitive, and every attempt to unveil dark matter's identity has so far deepened the mystery. If you could somehow see the Milky Way's dark halo, it would appear as a ghostly spherical haze engulfing the galaxy, a cosmic fog of invisible gravity. The luminous disk of stars would float like a fragile core within an enormous unseen sphere that dictates its fate. The terrifying realization is that everything we can see, every star, every planet, every nebula, is just a tiny luminous frosting on a vast invisible gravitational skeleton. Dark matter halos are not just structures, they are the scaffolding of the cosmos. They govern how galaxies form, merge, and evolve. Without them, the universe would have remained a thin, featureless mist after the Big Bang, with no galaxies, no stars, and no life. The invisible truly rules the visible. Yet, for all our progress, dark matter remains untouchable, unreachable, and unknowable. A silent force that shapes everything while hiding in total darkness. At the heart of this enigma lies an unsettling truth. The universe we perceive, filled with glowing galaxies, blazing stars, and radiant nebulae, is merely the visible residue of a much greater, unseen reality. The cosmos we inhabit is haunted by an invisible dominion, and dark matter halos are its shadowy kings. Neutron star collisions. When two neutron stars spiral toward each other, they create one of the most violent and terrifying spectacles in the universe, a kilonova. These collisions are not just powerful explosions, they are the literal forging grounds of the heaviest elements in existence. Gold, platinum, uranium, all owe their existence to the incomprehensible forces unleashed when two collapsed stellar cores finally meet. Each neutron star is the remnant of a massive star that exploded in a supernova. Containing more mass than our sun, compressed into a sphere only 20 kilometers across, a single teaspoon of neutron star material weighs billions of tons. When two such objects orbit each other, they gradually lose energy through gravitational waves, ripples in space-time that Einstein predicted a century ago, and which were first detected from such a merger in 2017. As the stars draw closer, their orbital speeds approach a significant fraction of the speed of light. Tidal forces tear fragments of neutron-rich material from their surfaces, and the surrounding space becomes flooded with intense gamma radiation. When they finally collide, the impact releases more energy in a few seconds than our sun will produce over its entire lifetime. The aftermath is apocalyptic. A brief, blinding flash of light, brighter than an entire galaxy, flares into existence before fading into darkness. The dense debris expands outward, creating radioactive elements that glow with eerie, fading luminosity. What remains may be a larger neutron star, or a newborn black hole, surrounded by a maelstrom of twisted magnetic fields and debris. If such a collision occurred within a few dozen light-years of Earth, its gamma-ray pulse could strip away our atmosphere, boil oceans, and sterilize the planet within seconds. The universe hides these cataclysms in distant corners, and for good reason. Cosmic strings. Cosmic strings represent one of the most chilling theoretical relics from the universe's birth. Ultra-thin, ultra-dense filaments of energy stretching across the cosmos. These structures, if they exist, are believed to have formed fractions of a second after the Big Bang, when the universe underwent rapid phase transitions and the very fabric of space-time cracked, leaving behind long, stable defects. A single cosmic string could be thinner than a proton, yet denser than an entire mountain. Just 1 kilometer of such a string could outweigh Earth. The gravitational field surrounding these filaments would be so intense that they could bend light, warp space, and even create gravitational lensing effects, where distant stars or galaxies appear duplicated or distorted. If two cosmic strings ever collided or crossed, they could reconnect and release massive bursts of gravitational radiation, sending ripples through space-time powerful enough to be detected across billions of light-years. Some scientists believe these events might be responsible for unexplained bursts of energy or gravitational anomalies that modern detectors occasionally pick up. The most unsettling possibility lies in what would happen if a cosmic string ever passed near our solar system. Its enormous gravitational pull could tear apart planetary orbits, slice through stars, and distort the shape of space-time itself, all without emitting light or heat. It would appear out of nowhere, invisible yet catastrophic, altering everything in its path before vanishing into the cosmic darkness. While no direct evidence of cosmic strings has yet been found, their existence remains theoretically plausible within modern physics. If they are real, they are relic scars of creation, vast, unseen filaments threading the universe like cracks in glass, each one carrying unimaginable power from the dawn of time itself. Quasar jets. Quasar jets are among the most awe-inspiring and terrifying phenomena in the universe. They are colossal beams of energy and matter launched from the centers of galaxies, powered by supermassive black holes that devour surrounding material. As gas and dust spiral inward toward the black hole, the immense gravitational and magnetic forces generate twin jets that shoot outward from the galactic core at nearly the speed of light. Each jet can extend for millions of light years, longer than entire galaxies. Within them, charged particles are accelerated to relativistic speeds, producing intense radiation across the electromagnetic spectrum, from radio waves to deadly gamma rays. The brightness of a single quasar jet can outshine every star in its host galaxy combined, making quasars some of the most luminous objects in the cosmos. What makes quasar jets so frightening is their destructive potential. The radiation and high-energy particles they emit are capable of sterilizing vast regions of space, erasing the possibility of life on nearby planets. If a quasar jet were ever pointed toward Earth from within our galactic neighborhood, the resulting blast of radiation could strip away the atmosphere and destroy all biological molecules in seconds. Even more unsettling is their scale and duration. Some quasar jets have been active for tens of millions of years, continuously reshaping their galaxies and the intergalactic medium around them. They sculpt enormous cavities in surrounding gas, trigger or extinguish the star formation, and even alter the evolution of entire galaxy clusters. At the heart of each jet lies an unimaginable paradox, chaos born from order, a perfectly aligned, focused beam of annihilation, powered by a black hole's hunger, beautiful, brilliant, and utterly lethal. Quasar jets are the universe's way of reminding us how thin the line between creation and destruction truly is. Gamma-ray bursts. Gamma-ray bursts, GRBs, are the most powerful explosions known to science. Brief, blinding flashes of high-energy radiation that can outshine every star in the universe combined, lasting anywhere from a few milliseconds to several minutes. These cosmic detonations release more energy in their short lifespan than our sun will emit over 10 billion years. GRBs are thought to occur during the collapse of massive stars into black holes or the collision of neutron stars. In either case, the collapsing object forms twin jets of plasma that punch through surrounding material at nearly the speed of light. When one of these jets happens to be aimed directly at Earth, we witness a burst so bright it can temporarily overwhelm our most sensitive detectors, even from billions of light years away. The radiation emitted during a gamma-ray burst is unimaginably intense. Within seconds, a nearby burst could strip away a planet's ozone layer, ignite its atmosphere, and vaporize its surface. Astronomers believe that ancient gamma-ray bursts may have caused mass extinctions in Earth's distant past, sterilizing large portions of the planet before life could recover. The afterglow of a GRB lingers for days or weeks, radiating across the electromagnetic spectrum, X-rays, visible light, and radio waves, as the jets interact with interstellar gas. Even long after the initial flash fades, the surrounding space remains scorched and reshaped by the sheer force of the explosion. What makes gamma-ray bursts so unsettling is their randomness. They can occur anywhere, at any time, and we would have no warning. Invisible until the final moment, they represent the rawest form of cosmic violence, silent, distant, and yet powerful enough to erase worlds across unimaginable distances in the blink of an eye.